Okay, so Professor Yuval Shavitt is a professor of electrical engineering at Tel Aviv University. Before joining Tel Aviv University, he worked for 4 years at the networking center of Bell Labs in New Jersey. He published semi-live papers in the field of changing, routing, and network measurements. In 2004, he established BG Project, a company that protects nation and large organization against IP hijack attacks. So please, Yuval.
Thank you. How would I find... somehow lost my where's the desktop? This is okay. Okay, hi, it's great being here. So I'm going to talk about traffic classification, and traffic classification is somewhat a loaded subject because while it has important engineering reasons to do it, there are also things that can be used either by law enforcement or by criminals in order to do bad stuff. So we need to be careful with this technology. So what I'm talking about, what I mean by classification, basically there's a flow of traffic in the internet, and I want to know what is going on in it. What is this flow? Is it a video call? Is it a chat? Is it a download of a file? If this is a chat, is it somebody using WhatsApp or maybe Messenger? So I might want to know what type of application it is. So this is a difficult task. In the good old days, many, many years ago, nothing was encrypted. You can just look at the traffic, read what it is, and know what's going on. There was also a usage of well-known port numbers that would allow you to, even without looking at the traffic, just know what application is in use. All these things doesn't work anymore. So we can look about the following scenario. And what you see here, by the way, is a true example that we discovered in the company where traffic during the German election, traffic to one of the the Socialist Party in Germany was diverted from London to Germany through New York. And you can imagine that somebody here in New York now looks at all this traffic. The thing is that we're talking about many, many flows, maybe hundreds of thousands of flows that are flowing now through New York, and these are all encrypted. And if I want to spend efforts, time, money, in order to decrypt this, I don't want to do this for all those hundreds of thousands of flows, only for those that are of interest for me. So I want to classify, I want to be able to say with high confidence, where should I put my efforts in? So this is what we are doing. This is just, of course, one usage case. So how would people do classification before we start looking at this? One thing was people were saying, yeah, let's let's do some kind of AI thing on it. Yeah. So there's something called feature extraction. I'm going to look at the traffic and I'm going to decide what are the important features I can still learn from the traffic. And then I'm going to try and teach my AI system how to identify the one that I'm interested in. It doesn't work very well. It needs a lot of human thinking, and humans are not so good at this. In the industry, people are using what is called reverse engineering. It's good for traffic that is not passing through serious encryption like what we do with VPNs. And what they do is they take a team of well-paid engineers. They work for a few months on a single application, and they manage to reverse engineer it to a degree that they can identify that this is indeed this application, and also what this application is doing at each moment. So this is really powerful. The only problem here is that if the application, say WhatsApp, is changing somewhat its protocol, you need to go back almost from scratch to do this reverse engineering. So you put a lot of effort in something, and it's like buying meat, you know. There's timestamp on it, and it's going to go rotten in a while. So we were looking to do something which is more robust. That's something that can work not only on regular traffic, but also traffic that goes through VPNs, maybe through Tor, and be able to at least identify what type of traffic it is. And what we didn't want to do is we didn't want to have the same problem of reverse engineering. That for every type of classification we want to do, we need to invent a new way of doing these things. So we wanted some generic approach that will work with everything. Of course, once you're going to engineer this, you're going to need to, you want to get this extra 2% or 0.5%, you're going to need to do maybe some engineering. But the idea was that a robust system that will give you good results will be generic enough, regardless of what type of classification you want to do. The other thing you want to do is you want it to work, to be easy to deploy, so you want it to work not on both directions of the traffic. And why? Because in many, many cases, you already have access to one direction. Even if you have access to both directions, taking packets from both directions and merge them together to a single location is difficult. You also want to use as little information as possible. You don't want to look at the payload. If you're a law enforcement authority, agency, if you just look at the metadata of your packets, from the legal point of view, it's easier than if you actually need to look at the payload. So, for example, if this is a police force, it could have been in some places that to look at the payload, you need the authorization of a judge, but if you just look at the metadata, maybe you just need the chief lawyer of the police force or something like this. So it's easier for you from an operational point of view to do. So this is another thing you want to do. And the other thing is we want it to be fast. We don't want to wait an hour till we classify, because maybe you want to intercept, say, a terrorist organization that is planning something. You want to see gets this thing in real time. And so when we thought about, applying AI into it, and we were immediately thinking about CNN, convolutional neural networks, deep learning. There are lots of ways to do those things. And instead of trying to invent a new way, we were looking around asking ourselves, what is the most successful applications of this technology? I mean, you look around, you see that the one field where it's really, really successful is in picture classification. They can identify cats from dogs, and it's really, really nice. You look at all this demonstration. They can identify people. If you look at Google, they identify you in posts. It's really, really strong. So we thought about it that it might be really, really great if we can take our problem, a networking problem, and transform it into a picture. And this is what we did. And we call it FlowPic. So we take the packets in some time window, transform it into a picture. We run the picture into a standard, almost standard, picture classification CNN, and we get classification. I'm going to give you some more details. So the idea is first you take an interval. The interval can be quite short, as short as 15 seconds. And you take all the packets in this interval. For each packet, you take just two numbers, the time of arrival and the packet size. So you have two directions, X, Y, this is the picture, and each pixel in the picture counts how many packets arrive at this time period with this size. And you get the picture on the right there. There's some technical details I'm going to skip. So what I show here are some examples of how different applications look like. So let's look at voice over IP, yeah? Voice conversation on the internet. On the top left, you see a regular VoIP. Like you see lots of packets with small sizes, nothing with large sizes. You see it's cut about at 200. Does this work? Yeah, we're talking here. You take the same application, you run it through a VPN for better encryption, and it looks a bit, it's quite similar. You know, there's more size distribution here, but still very small sizes. Then you take the same application and run it through Tor in order to disguise who you are, where you're coming from. And yeah, it looks different, a lot different. You do the same for another application. This is VoIP, video, for example. You see that the spread of sizes is large. Of course, most packets are of a certain size, around 1,400 bytes. You pass it through VPN, looks different. You pass it through Tor, looks different. And there are more examples here. So what we want is to be able to identify all these types of pictures by CNN and classify them. Now, you think it's easy, but if you look at different applications, they don't look the same. For example, what you see here are different video applications. So you see Facebook, Google Hangouts, Netflix, YouTube, Vimeo, and Skype. And while some of them look quite similar, some of them are quite different. So if you want me just to identify that some application is a video application, there's a big variety. So just a few technical details. I don't want to go deep into it, just want to kind of bring you into the system. So basically, a neural network is based on artificial neurons that basically get multiple inputs. They do some kind of function and so moving it through some a threshold and get an output. Typically, they are built in multi-layers. So there's the input layer and the output layer, but in between there are many, many layers, depends on the specific design. Each additional layer adds to the complexity of the network. And you have to understand that at the end, what we need to do is we need to learn the weights of all these arrows. So all these arrows are connection, and each connection has to be weight. The more layers you have, the more connectivity you have. You need to learn more numbers, and it's become a very difficult task. I just want to show you a few techniques of what these layers are doing. So this one, for example, we take a large image, and we take blocks in this image, and we multiply them by zeros or one. They are called the kernel. And as a result, and we multiply in sum, we get a smaller picture with numbers. So this is called the convolutional layer. The other thing we can do is something called max pooling. So you take a picture, or it's already not a picture, it's something that was done after you did convolution. And for each block, say a 2x2 block, we take just the maximum number. Because we don't care about the small signal. So you do this, and this is the network we choose to use here. And the result, we ended up with roughly 300,000 parameters to learn. These are the weights of those arrows connecting the layers. It's not a small number, it's not a huge number. It's a good trade-off. To see that what we're doing is really meaningful, we need data. For this, we use data from the University of New Brunswick in Canada. They did a lot of work in labeling many flows going through various type of encryptions and, of course, various application types. The data set was not good enough for all applications, so we had to generate some of our own in order to enrich this data set. And this is the end result. So we have these 5 types of application. You see in each type what application they did, and some of them we did. And as you can see, there are some that are going not through a VPN, just, they're encrypted, but the IP is still the same IP. There are some going through a VPN and some going through Tor. This is the number we got. So some of the things we did with the first thing we wanted to do, some we just improved on previous work. So what we did first is what we call multi-class classification. The idea is that you have a flow, you have multiple classes of type of application or the application itself, and you need to say which of the type you're seeing. So if there are 10 types, you have to say this is X or Y or Z, W. The other thing is to be able to identify what encryption is in use and the application. The other type of experiment we did is to identify a certain class. In many cases, if you are law enforcement, for example, and you're interested in VoIP, so you don't care about the rest. You just say, tell me what is VoIP. This is what we call class versus all, and we did it for 5 classes and also for the for class against all. And finally, I'll show you results about classification of unknown application, which is just so how strong these results are. So about the evaluation criteria, usually we use accuracy, which is the number of true positive versus true positive plus false positives. There are other criteria people are using, like recall, for example, and persistence. So let's first look at traffic categorization results. Here, what we're doing is we're trying to identify the application, again, multi-class. And as you can see, if you just want to do what is the top classification for the application, we get about 85% accuracy. This is out of 5 categories. However, if we say, okay, if we're ready to take the top 2 classifications, so not just what is the first peak of the CNN, but what is the second peak also, then it goes up to 99%. And if you do it through VPN, it's even better. I think what happened there is that the data is just easier for us. For Tor, the number is not great, but remember, Tor is very, very difficult. We are the only ones in the world that actually tried even to do something with Tor. So this is really a great result. And overall, we got these results. So this is a classification of type of classic. What you see here is more data, and this is really interesting. What we show here is, how do you read this? So suppose you want to identify VoIP, okay? You train it on VoIP without VPN, and then you test it without VPN. You get to 99.6% accuracy. It's great. Now you take the same training. You don't retrain, and you test this training on something that goes through VPN. Remember, the CNN didn't see traffic through VPN. You still get to 99.4% accuracy. So although we didn't train it to identify VPN, it still manages to do it with extremely high accuracy. It doesn't work all the time, yeah? For example, here with video, if we train it on VPN and you pass it through something that didn't go through VPN, we get only 54%. But if we test it on what we train it, we get 99.9. And yeah, even in Tor, we're getting quite good results. Yeah, these are these numbers here. So only for file transfer we don't, but So these are really, really great results. The second thing is that I want to show you is classification of unknown applications. So the idea here is the following. We know that application designers keep changing the protocol. You train it on, say, Skype VoIP. Next month, there's a new version, and it doesn't look the same. Do we need to retrain everything? Do we need to redo everything? So in order to test this, what we do is that we train our CNNs, for example, to identify video, but we excluded Facebook video from the training. Now we tested it on Facebook video, and we still got 99.9%. It was close enough to the other applications, so the CNN could identify it. We repeated this experiment for VoIP with Facebook VoIP, and again, we got 96.3%. So all in all, the system can identify with high accuracy application type, regardless of the version, regardless of the specific application. And this is the first time somebody actually do something like this. We can also identify the type of encryption. VPN is sometimes mistaken to be non-VPN, but Tor, of course, is easy to identify. This is not a surprise. And we also tested this to see if we can identify exactly what application. What we see here is 10 applications, all VoIP and video. And the system needs to identify which one of the application we're seeing. Remember that the random classifier would give you 10% accuracy. You see that we're almost 100% accuracy along the line. There are very few. There's one case with which we are a bit less. So here we are at about 89.9 or something like this. But other than this, it's almost perfect. We repeated this also for traffic going through VPN. We got the same results. Same results, only 5 applications because we didn't have enough data. But 5 VoIP and video applications all identify it close to 100% accuracy. These are remarkable results. Of course, we can do future improvement to this mostly in terms of engineering and size. I don't want to go into it. What I do want to say in a few words is what we are start doing right now using same techniques. The idea is that we take similar CNNs, not the same, similar one, and we feed it with BGP announcement. These are the announcements used by the Internet Routing Protocol. We also add trace route measurement. This is, again, measuring routing in the Internet. And the result is classification that can help us, at the end, save the Internet. So what can we do? We can identify the network type. We can identify the relationship between between neighboring networks. Other peer-to-peer, other provider and customer, other belonging to the same company. And we can feed the CNN with a route, and it can identify if it is being hijacked or not with an accuracy which is close to 100%. So this is work in progress. We are now wrapping this up for a paper, and I will be happy to talk about it next year on the AI session. Questions? Yep. Well, first of all, I want to remind you that not all the applications are related to catching bad guys. There are traffic engineering reasons to do this. So, but even if this, most people are not aware of these things. So even if they know about it, if you're a random terrorist using a PC somewhere and you're using WhatsApp to communicate to your friends, it is not clear that you have the capability to change how WhatsApp behaves. There might be some, application that will go, and then it will give us a problem. Yes, you're right. But yes. The quality, you say, the quality of the voice. I've never thought about this. It would probably be quite hard, but maybe not. It depends how these things affect those parameters that we are looking at, timing and size? I don't know. Maybe they do, and maybe it's an easy task. Maybe it's an impossible task. Before you try and look at examples, I cannot really say anything. Yeah. No, it's not. Not anymore. It used to be that people would use well-known port numbers. This is what you mean? Now everything is over port 80. Nobody is using port numbers anymore. Yes. Well, the location, if you're not using VPN, your IP tells me where your location is. Especially if you're law enforcement and you can actually go to the provider and tell them, I need to know where this IP was in this time, and then they know. If you're using VPN, it's harder. Yes. Yes. If I can do better than 99.9, or yeah, actually you can. Obviously, you can have side information, which is easy to, for example, the IP numbers of the server you're communicating with. It will increase you to close to 100 because in many cases those servers are well known. So yeah, if you add side information, yeah, you can do a lot better. Looking at the content, usually without content. No, I'm talking about IP numbers. So you just add IP numbers to the equation, and you're going to be a lot better. Yeah. But why would WhatsApp want to do this? It can. But then, if there's going to be one application that is adding random noise, I can probably identify it according to this. If everybody is going to do it, yeah. But if you think about it, Tor is almost like random. And in some cases, even without training Tor, we can identify Tor. So it's not as easy as people think. Yes, Adia? So, yeah, some of them were using CNN, some of them were using other learning techniques. But yeah, the majority were using all sorts of CNNs. Yeah. All right. I don't know where they get where they example the data. I assume it's in the first hop, but I don't know. I'll have to go and look at the. I don't know if it is mentioned in the paper, in the New Brunswick paper. I don't know. Okay. Excuse me, I didn't hear you. No, not on the call. No, we're looking at the packet. It's a pickup file, basically pickup file. Okay, I guess this is the end of the session. Thank you very much.